Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Talk for this session this morning, focusing on memory and garbage collection issues, will be given by Sebastian Marion. Sebastian and Richard Jones are visiting us from the University of Kent. Richard is the Deputy Director and Senior Lecturer in the Department of Computer Science at the University of Kent, and was made Honorary Fellow at the University of Glasgow in July of 2005, which he notes is the only computer scientist to receive this accolade. His chief areas of interest are dynamic memory management, particularly object demographics, GC for distributed and for persistent systems, measurement and visualization of heap-based allocation relevant to this work, flexible GC for very large heaps, VM support for garbage collection, and cache behavior of GC programs. Sebastian is currently doing a PhD in the area of garbage collection at the University of Kent under Richard, and his project work for Rotor consisted of integrating a heap visualizer into Rotor called GCspy, and that's the focus of this talk.
All right, good morning. So yeah, as Mark said, I'm Sebastian. I'm working with Richard Jones. So we'll be talking about GCspy, which is a heap visualization framework. Right, so this framework was developed by Richard Jones and Tony Pruntices. Well, this is a small screenshot of the application, but we'll come back to it later. Right, so this is the plan of this presentation. So first of all, we'll talk about the motivations and the requirements of this project. What are the abstractions and the architecture of GCspy? What are the benefits of this application? Then we'll move to our Rotor implementation of GCspy. Then we'll talk a bit about some new views which have been developed for GCspy, and eventually we'll conclude. Right. So the motivation of having this kind of visualization tools is because GCs have chaotic behavior. It's really hard to understand really what the GC is doing. So with this kind of tool, the GC developer can have a good picture of what's happening inside the heap. So yeah, visualization, it allows so concise insight into the GC behavior, and it enables you to profile and easily debug the application. Right. So we believe this kind of framework should be portable and adaptable to easily to any virtual machine and eventually any operating system. Should be easily extensible, so with some mechanism for plugins or whatever. Should be scalable to any heap size, small heap size or huge heap size, whatever. And it should be, of course, responsive. Right, so this is a few abstractions available. Well, this is the abstractions available on GCspy. So on the GC side, you've got some components such as generation, so nursery space, nursery or mature space or whatever. And yeah, this is visualized as a space in the visualizer. On the GC, you've got also blocks of memory. We visualize them as tiles in the visualizer. You've got some attributes such as the use space or the free list or whatever, which are visualized as streams in the visualizer. And eventually you've got some events such as start of mark phase, end of mark phase, whatever. Right, so this is a framework of the application. So this is a fairly generic view. So basically you've got the application here, which is sitting on top of the virtual machine. In the virtual machine, you can have a copy GC and a max with GC. They are triggering data collections. So this is fairly generic part, while the copy GC and MSGC, of course, are dependent on the virtual machine implementation. This data collection is relying on copy drivers and max sweep drivers. So this has to be developed specifically for the virtual machine. That's actually mostly the only only thing which has to be specific to the virtual machine. So in the copy driver, you have, well, you can have used routes, while you can have object cards marked in a MaxWeb driver. All that is relying on the server interpreter, which is generic in GCspy and which is talking to at the communication level. So then the virtual machine is communicating with the client here through a socket. And eventually, the communication are going up and are interpreted by the client interpreter, moved on to the spaces, eventually rendered and then visualized. Right. So this is a screenshot of what you can get with GCspy. So here you've got some, well, you've got the event. So you can see this screenshot was taken before a nursery collection. But it could be after nursery collection, whatever, so the program will tell you. In here, we've got 6 different spaces available. So we've got a nursery space, a mature space by size classes, and the free list for mature spaces, and so on. So they're all visualized in separate places. You've got 8 streams. So those streams enable you to refine which view of the space you want to really see. So you can want to visualize the scalar use space stream or the array object stream of the space or whatever. It's up to you. You've got a magnifier, which is mostly zooming option. You've got some tile information. So for every blocks in here, we can see this block is selected. So you can have information such as the number of scalars or the block size or whatever. Right. So in the nursery space, this is an Apple-style nursery space collector. So the separator shows the history. So basically, the Apple-style nursery collector means that at the beginning of the program, the nursery space is taking the entire heap. And when a collection is triggered, some objects are promoted into the mature space. And this space, so the mature space is growing. And while the mature space is growing, of course, the nursery space is shrinking. Right. So you've got the history of what happened. You've got some view selectors, such as history, text, or histograms. This is plugins which can be developed separately. Right, so this is a history view of the mature MaxWeb space. So you can see for a long time it's been at the same, the mature space has been the same size, and then eventually it started growing. This is a histogram view of the mature spaces free list. So you can click on a bar and get information about the cells. So basically here you've got the number of objects. So you can know the number of objects of 8 bytes or whatever. As you can see here, there's ... which basically means there are more objects than our limit. Right, I'll quickly talk about the CLR profiler, which is another tool available. So it's available since 2003 for the .NET platform. It's intended for application developer. It provides some detailed exploration and of the application's memory behavior. And it provides different views, nice views actually. But it's got some drawbacks. It can slow down the program execution from 10 to 100 times, which is absolutely huge. It creates big log files, which can consume gigabytes of space. It needs the application to be compiled in a special mode, and it's only available for .NET on Windows. So on the other hand, what are the GCspy benefits? So GCspy is loosely coupled to the VM. So you can rapidly develop some visualization of new algorithms. You can visualize a variety of data structures, such as card tables, free lists, trains. You can connect and disconnect from the virtual machine on the fly. So this is really interesting. So you've got on the VM part, you've got a socket listening to listening for connection, and you can connect anytime and disconnect. You've got almost no overhead outside data gathering periods. So basically, if the client is disconnected, you will have almost no overhead on the application. So GCspy has been developed for very large heaps, and it provides some small trace files that you can easily store and replay. This is really useful because it's really hard sometimes to do this, to have the same memory behavior two times with the same program, because it depends on a lot of inputs, etc. So you can store the trace and eventually replay it to see what happened. I'll introduce RMTK. So basically, it's been a bit introduced by Anthony. So RMTK is it's a part of MMTK to Rotor. So MMTK is a memory management toolkit. So it's an extensible and portable framework which enables the builds of garbage collectors. It was originally developed by JVMs. So RMTK is the port of MMTK to Rotor, done by Andrew Gray. So it relies on GCJ, which is a Java compiler. So it compiles into machine code rather than byte code. And then it enables us to talk from the C++ world to the Java world. So why did we choose RMTK? Because it provides a wider range of GCs. And you can easily implement new GCs. So at the moment, we've got a mark sweep collector implemented, a Smith-based copying collector implemented. We've got a generational copying collector implemented, which copy both generations, the mature space and the nursery space. We've got a generational mark sweep collector, which is copying the young generation and mark sweeping the old generation. So actually, all those collectors have been instrumented with GCspy. So our Rotor implementations, so we provide the use of different GCs, so you can easily choose which GC you want to use according to your application, because with some applications, some GCs perform better than others, so you've got the choice. You're required to build, one build per GC, so basically if you want the 4 GCs, you need 4 builds. We provide the possibility to compile with or without GCspy support, with MMTK optimization turned on or turned off. The build is creating one RMTK library per collector, which contains the GCspy drivers specific to the collector, and adds wrappers to handle the communication between RMTK and GCspy. And eventually, on the other hand, you've got only one GCspy server library, which is generic. Right, so this is the MMTK's integration into Rotor. So as we saw, while Rotor has a copy GC and a mark sweep GC, this is replaced by MMTK GCs. So in our picture, it's replaced by a copy driver and a mark sweep driver, but actually we've got more than that, and you can almost add anything you want. So yeah, so this is the MMTK's integration. Right, so for the data collection, GCspy, we're doing it in synchronous mode, so basically it's a stop-the-world GC, but you could do it asynchronously if you want to. Yeah, so you've got other methods possible. Right, so I'll talk about the components integrations of our project. So first of all, you've got the RMTK part. So in this RMTK part, you've got MMTK, which is transformed and built into JMTK build. You've got some GCJ specific code, which is built into JMTK as well. All that comes to produce the RMTK library, which contains the GCspy glue code. Here, you've got the GCspy specific code. So you've got the client and the server. The server is creating a library called libgcspy, which is talking to the client through the socket. and which is communicating with the GCspy glue, so with the RMTK library. So that's how we get the information from the framework. Then you've got the modified version of Rotor, which contains several components. One of them is a virtual machine, of course, in which we're interested. So the virtual machine talks to the RMTK library, and the RMTK library to the GCspy library. So that's basically how our framework works. So yeah, the components instrumented. So we've instrumented a variety of data structures, such as copy space, so with contiguous allocation, markup spaces, remembered sets, segregated free lists. Right, now the GCspy client. One of the goals of this project was to develop new plugins view mechanism. So it's been developed. So it allows you an easy development on the incorporation of new views. So as we saw, we've got history views, histograms, etc. But you can add some new views. It's fairly easy to add a new plugin. Basically, you have to extend a class called plugin listener, which is pretty trivial, about 9 lines of code. You have to extend a plugin frame. This depends on the complexity of your view. If you want something really complicated, of course, you'll have to write complicated code. It depends on your plugin. All that just needs to be saved as a jar files in the plugins directory. Then the plugin manager will discover all the available plugins at runtime. And it maintains a list of the activated plugins and the menu to choose which one to enable or disable. Right, so concerning benchmarks, it's not easy at the moment to find benchmarks available for the .NET platform, so C# benchmarks. We've got some benchmarks by Benzone and Sandra Krins, which are available. So synthetic programs are okay for stress tests, but real programs would be good to get a real understanding of the application. And they would be good if they're documented and open source. Right, so our methodology. So we did some experiments. These experiments, we did them using the RMTK framework without GCspy, using the RMTK framework, using GCspy compiled in, but the GCspy client disconnected, using RMTK and GCspy compiled in and GCspy client connected. When this is the case, we're doing some object-level data acquisition. So the performance overhead. When the GCspy client is connected, we've got a fairly low average overhead of 8.47%. We get to 36% in the worst case in the benchmarks we tried out. So while the GCspy client is disconnected, we've got a really low overhead of 2.5% in average. So this is fairly small. Right. But we have to point out that RMTK is actually fairly slower than the native Rotor implementation. Right, so this is some performance charts. So in orange, you've got all the GenMS, general mark sweep benchmarks, while in blue, you've got the GenCopy. So this is the GenMS natural. This is GenMS implemented with GCspy, but GCspy client disconnected. And this is GCspy with GCspy client connected. So you can see the overhead is fairly small. This is the optimized versions of the previous ones, so we get much better performance. So this is for the ray tracer benchmark, and this is for LCS benchmark. So as you can see, well, the overhead is pretty low. So I'll go to I'll conclude. So GCspy has been incorporated into Rotor through RMTK. We've got several GC implemented. We've got 4 of them, which are all working with GCspy. So it's easy to develop new GCs for the Rotor platform. We've got new GCspy views available. We've got good performance results. The server API has been documented, as well as the GCspy client. And eventually some interesting benchmark would be good. Right, so I'll do a demonstration quickly. Right, so we'll play a trace. So we're going to play the GenMS trace of GCspy, of GCbench, sorry. So this has been recording from our Rotor implementation. So then we'll launch the GCspy client. You have to notice that we're going to replay this trace, but we're actually, every second a new event is happening. This is not what was recorded, but that's just for the purpose of the presentation that we're making it faster. But you can have it in real time, of course. Right, so you've got the plugins menu that you can choose what to enable, so we're going to enable all of them. Then you connect to the application to the play trace facility, which is waiting for connection. Right. So I posed the GCspy client. So you've got all these spaces which are directly recorded from the trace file. This is not hardwired into the GCspy client. This is taken at runtime from the virtual machine. Right. So this is the nursery space. We're going to do well, yeah, we can do a histogram of the. Sorry, we're going to do a history of the major space. So we'll start recording. We'll take a histogram of the free list, right? And then, okay, let's start. Right, so you can see the nursery space is filling in. Some objects have been promoted to the major space. Then the nursery space has shrinked a bit, and it's doing so it's collecting. So at the moment, you can see in the nursery space, most objects are collected and not promoted, right? So in the history view, you've got what's happening exactly. So this is a replay of the major space. So you can see that it's not growing. It should start growing soon. So here you've got a histogram of the different objects. So you can see how many objects of which size are available, right? So you can see that there's been a promotion of objects because the nursery space is a bit shrinking, right? So now the major space is growing, so you can see exactly what's going on. You can have information for different spaces. So this is the information for this space. You can have information for the major space by size classes if you want to. This is the different views available. So array use space stream is empty. So yeah, you've got different things available. Right, and this is the magnification tool, so it's mostly just a zooming option. So we can do it for the major space. Right, so the trace is over. Right, so that's the end of my talk. Is there any questions? Sorry, yeah.
Is there a way to trigger based upon some specific event? I mean, I imagine there's a lot of data I'm getting here, but I might be interested in a specific scenario where, say, the nursery grows to or shrinks to a particular size.
Well, at the moment, you can't trigger, well, you can't pass events from the visualizer to the virtual machine. It's only mostly one way visualizing.
But you could filter which events you're interested in. So you could say only gather data when there's at the start of a mature space collection.
Okay.
But you can't do things like trigger heat dumps on the fly or whatever.
Okay.
But we thought about that.
Thank you very much.